Hello and welcome to this Topics in Depth video. My name's Craig Barton and I'm delighted to be joined by my co-host Joe Morgan. Hello Joe, how are you?
Hi Craig, I'm very well, thank you.
That's good to hear. Right, we are delighted to say that Topics in Depth is proudly supported by our friends at AQA. Quick notice, AQA is not responsible for the content or any third-party material in this video, save for the use of its past examination questions. Right, Joe, 3 questions for you. Are you ready?
Yes.
Question number 1, what's Topics in Depth all about? Question 2, how might a teacher use the material in this video? And question number 3, what topic are we going deep into today?
Right, so Topics in Depth is a project I've been working on for a number of years where I realised that teachers would really benefit from looking at a topic in depth before they teach it, so that they can then teach it in depth to their students. Because I realise that a lot of maths teaching involves, or used to involve, rushing through topics really quickly, sort of scratching the surface. So I think teachers need to spend time teaching topics, but they can't do that if they don't know really well the curriculum, how it's assessed, the history, the resources, all those things. So I've made a series of CPD sessions that teachers can use. How can they use it? Well, one big recommendation for me is in department meetings. So say, for example, everyone's going to be teaching the same topic to year 8 next week, then a head of maths or a maths teacher could run this video in a department meeting, or they could perhaps use my slides and adapt them and go through it with the team. And then everyone goes into that topic really confident that they know it really well before they get started. So today we are going to be looking at area.
Oh, nice.
Yeah, and area is obviously a fantastic topic with lots and lots to it. So, you know, because we've got circles, we've got triangles, we've got some trig, but we're going to focus on just specifically a few bits of area. So focusing mainly on trapeziums, triangles, that kind of thing. So we're not going to be talking about circles today. We're not going to be going beyond, so we're not going to be doing sort of trigonometry. So we're going to focus, because that means we can go into depth if we focus on quite a small bit of this topic.
Got it. All right, let's get started then.
Right, so the bit of history.
You love a bit of history.
I do love a bit of history. It's so interesting. And also I think the students find it interesting. You know, I quite often in my lesson, it's not like I spend ages on it, but I'll spend a few minutes talking about the history, and the students are always like, wow, they never even thought of maths beyond the maths they're doing right now. So just to sort of understand how it fits in is really nice for them. Area, you know, it's kind of everywhere, you know, so it's something that has always existed. But it was one of the most ancient problems, was measuring land area.
Okay.
So, you know, this is one of these things where this bit of maths goes back a long way, where people needed to assess how much land they had. So it makes sense that in terms of things you do in geometry, understanding area is a very ancient thing. So we're talking sort of ancient Babylon, ancient Greece, ancient Egypt. There's evidence of calculations of area. And if you have a look at the image there, so that is an ancient Babylonian tablet, a stone tablet, with a area of a trapezium calculation sort of etched into it. And these are quite famous things that have been discovered. And the interesting thing is that on the tablet, it's incorrect, apparently. If you translate that from whatever language that's written in, apparently that's not the correct formula. Which suggests that maybe they didn't know what they were doing. But then someone has told me, since I've sort of been looking at this, I had a maths teacher come and say to me, by the way, did you know that there's evidence that these were students' homeworks and that's why it's incorrect? So they found kind of lots of these tablets in what might have been a classroom, and there's errors in them because this was perhaps students getting it wrong. So it's not necessarily that they didn't know how to work out the area trapezium, it's that it was just mistakes being made in ancient classrooms, perhaps. Now
they forgot the units. I can tell you that straight away.
That's all kind of allegedly. Like I don't know, like whether that definitely is a student's piece of work, but it is interesting to see them doing the same calculations our students do.
It is, and just on the wider point, like you're right, starting with some kind of history or anything like that just shows the kids that there's a bit of purpose to what we're doing, as opposed to trying to, you know, shoehorn it into some like dodgy real life context. I love a bit of looking back at the past, and it only takes a couple of minutes, and the kids love a bit of this.
Absolutely. I mean, it's one of these, you know, when are we going to find the average trapezium in our life? I'm not going to pretend that they will, but am I teaching them the best that has been thought and said, and like this sort of body of knowledge? Yes, I am, and that's the important thing.
Lovely, that.
And then this was another, you know, I like an old textbook.
Oh, God. If this was a drinking game, people would be hammered already. Joe and her old textbooks.
So
Yeah,
this
go on.
is Know Your Maths from 1957, so not that old.
No, okay.
But it says, when we wish to measure a length, we use a ruler or a measuring tape. To measure time, we use a watch or a clock.
Nice.
To measure weight, we use scales, but we don't measure area in that way. However, there is an instrument, and who knew? There is an instrument to
Wow.
measure area. It's called a planimeter or something. I don't know how you pronounce it.
We'll go with that.
But it's, yeah. Do you know what that looks like?
No,
A planimeter?
definitely
No, I didn't know what it looks like. I had to look up a picture. That's what it looks like. So that is an instrument for measuring area. I don't know how it works.
Jeez.
I looked up how it works, and it was
Okay.
very complicated. Lots of complicated.
Was it like electronic or something? Or?
Well, no, because these were around a long time ago, and I believe they're, well, it's a bit like sort of thing you get in a math set, but just more advanced. I don't know.
What, it's measuring the area of that?
I don't understand it. I looked it up, and I think there was all sorts of complicated calculus in the explanation of how it works.
Jeez.
But it's we don't use that. I don't think many people use that because we just calculate areas.
Yeah.
Obviously, that looks like it'd be useful, particularly for some kinds of shapes that we don't have a formula for. But yeah, who knew? Who knew
Wow,
there was an
definitely not
instrument?
me. There you go.
Yeah. So obviously, we don't use that. We use formulae to calculate area. So it's one of the things where we're measuring something without a measuring instrument in the classroom. We're using a formula instead.
Nice.
So what I'll do is I'll talk you through the curriculum.
Okay,
So
nice.
like where area comes up during secondary education, and I'm talking about the curriculum in England and Wales. So it doesn't necessarily the same curriculum in other countries.
Yep.
And then we'll look at some assessment and how it comes up in exams, particularly at GCSE, and then we'll look at some teaching elements.
Here we go.
So in terms of curriculum, year 4. So I've got a younger daughter in year 4, and I've seen her doing this. She's counting squares.
Nice,
So that's very much the concept. You know, they have such an important job in primary, don't they, of really embedding the concept of what area is. So, you know, you wouldn't want to go straight in with a formula. You want them to understand that it's a space taken up on a flat surface. So therefore, we're going to count squares. I've got my daughter doing that at the moment in year 4, and then in year 5 then they're going to go on and do looking at standard units. They understand that square meters, square centimeters, and I think it's worth saying there about, look, it is square meters, and a lot of people say meter squared or centimeter squared, which you do when you write it. Yes, it's centimetre squared, but these are square centimetres. And I think that was something that was a really interesting debate I saw online a while ago. Do you say centimetre squared or square centimetres?
Without any thoughts given to it whatsoever. I'm centimetres squared all the way.
Yeah, so I used to say that, and I sort of thought about it, and I thought, actually, they're square centimetres.
Right,
so now
okay,
I
I'll
always say
change
that.
that.
It's
Yeah,
like such
fair
a minor
point,
thing, but
fair
it was nice
point.
to see it there in the curriculum as square centimetres. And estimating areas of irregular shapes. So that's year 5. But when they get onto year 6, it's looking a lot more like secondary maths.
Right, okay.
And my older daughter's in year 6, and I can see her working out areas using formulae. So she'll say base times height or length times width.
Yes.
And again, that's a bit frustrating. There's 2 different ways of saying that. And then they also look a little bit of volume. And they also look at areas of parallelograms and triangles. So that's all done in year 6.
Just on that as well.
Yeah.
I mean, this comes up all the time, right? Like, it blows my mind as a secondary school practitioner how much stuff is covered in primary, right?
Yes.
And like, even though you're now completely familiar with the primary curriculum, it's still surprising, isn't it? When you look at that for year 6, what would essentially form a year 6 scheme of work, that will be covered in most year 7 and 8 schemes of work, right?
Absolutely, but so there's a few things there. First of all, they go through things pretty quickly in year 6 because the curriculum is so tightly packed at primary, so they don't get a particularly deep understanding of it. I mean, it's taught very well. Primary teachers are doing an amazing job, but primary teachers are having to rush, which is really means that we can then in year 7 say, well, now we're going to go into that in a bit more depth, and that's how I introduce everything now in year 7. And I'm very careful with my language. So when for example, I'm doing some fractions with year 7 at the moment. And I'll say to them, most of this is recap of what you've done in primary school. I'll say, I know that you did this in year 5 and year 6, and it helps having children at primary school, but also I've read the curriculum loads. I'm really confident in saying, I know you've done this before, but I do also know that none of you have, say, divided by a fraction before, because that's not on the primary curriculum. And I'll say to them, we're going to go into greater depth. We're going to look at some challenge. We're going to look at some different methods, and there's going to be a bit of new stuff along the way as well. So I say that a lot to them. So, for example, when I'm teaching multiplying fractions, I'll say, I know know you all multiplied fractions in year 6. I'm not. Some of you won't have seen, say, cross cancelling to make the simplification easier. Or I might say, how many of you have seen it before? And generally, that's about 5 or 6 of them. And I say, right, that's what we're going to focus on. So yeah, we do revisit these topics in year 7, but we go into greater depth and we look at them from a different perspective and we extend them and we bring in algebra. And actually, that's one of the nice things about area in year 7. Is that if you teach it after you've taught solving equations, then you're making it different. So you're not just repeating year 6. You're saying, right, you all know how to find the area of a triangle. We'll recap that quickly for those of you who've forgotten. But hey, let's say the area is this and that's an x. And, you know, they can do some equation solving.
Got it.
The questions at Key Stage 2 were always lovely. I really like
Come up with
reasoning.
some good ones, don't
Yeah, they
hey?
really
Wow.
do. The people that write the Key Stage 2 stats questions are really good. This one, we've got 2 shapes with the same perimeter, a hexagon and a square. The length of each side of the hexagon is 8 centimetres. So they find the area of the square. It's a nice question in terms of understanding the difference between area and perimeter, and then a little bit of reasoning along the way.
Just 2 marks stingy, isn't it?
Everything's not very many marks in stats. It's always quite surprising, so that's a typical question. Oh, I was going to mention on that. Let me just go back to that. Notice how the units are stated, and I think we've discussed this before in a podcast. They never have to state their own units in primary. So I remember we used to do a baseline test for our year 7s coming in, and we would say, and we had a couple of area questions in there. And it said state your units, and they had no idea what we meant by that. And we just thought that they've used units before, they've just never had the instructions state your units or write your units. So yeah, it's that's something that year 7 teachers need to be aware of. Anyway, this is what they get to in Key Stage 3. So obviously in Key Stage 3, the national curriculum it's not broken down into year group. But we're told they need to know area of triangles, parallelograms and trapezia, and then also circles and composite shapes. So like I said, in this session, we're not going to talk about circles. They used to have SATs at Key Stage 3, and that's a really good source of assessment questions. When I write Key Stage 3 assessments at my school, I'm always using the old SATs questions. They're really good. Have a look at this one. It's lovely. So on the grid, draw a right-angled triangle with an area of 12.
Nice,
So that, is fairly straightforward as long as they know that they, if that's 6 units along, they need to know that they shouldn't be going up by 2 units. That's the issue there. But then the part B of this question is lovely. Now they want an isosceles triangle with an area of 12, and they just need to know it's exactly the same height as the other triangle. And it's a really lovely question. And this is the kind of thing you get in these old lovely SATs papers. Another one, this was from Key Stage 3 SATs, and this one is way more advanced. This would be like, say, year 8, once they know how to expand double brackets. So they have the same area. So obviously you've got double brackets on the first one, double brackets on the second one. When you then equate them, the y-squareds cancel out. So this isn't a quadratics question. Like on the face of it, you think, are they going to have to solve a quadratic? But actually they're just solving an equation with a variable on both sides, and they're expanding brackets. So this question is just perfect to go and say, for my school, end of year 8 assessment, where they've done expanded double brackets and they've done solving equations, and they know how to work out an area. So what a nice question.
Nice.
Bit of interweaving there.
Yeah, it's lovely.
So back to curriculum, Key Stage 4, it always says, in addition to consolidating subject content from Key Stage 3. So we have to understand that Key Stage 4 is everything in Key Stage 3 plus some more. And there's nothing massively new in terms of the sort of triangles and trapeziums and parallelograms. There's bit of circle stuff, so arc lengths and sectors of circles, and then there's more in terms of surface area. But apart from that, it's very similar stuff to Key Stage 3.
I'll tell you what, I was just going to ask you on that. So like all your different quadrilaterals, so when you have like a kite and an arrow, are they just considered kind of composite shapes?
So I mean, I would see a kite as 2 triangles and even a parallelogram. So I guess they don't specify every type of quadrilateral, or like a rhombus or something. Ask a student. Like I had a question in our year 9 assessment recently. We asked the students to find the area of a hexagon, and it was they had to use trigonometry for it, and they hadn't done half A, B, sine, C, so they had to basically find heights of each of the 6 triangles. Really challenging question. We put it on there to stretch the students right at the top, but it was that's an example of, obviously nowhere in the curriculum does it say they have to find the area of a hexagon, but it is something that they should be able to do.
It's an important thing, right? Because you can imagine kids saying, well, I don't know the formula for area of a hexagon, or I don't know the formula for an area of a kite or whatever.
Yeah.
Okay, cool.
And then the other bits at Key Stage 4 to do with area are your half A, B, sine, C, which is, like I see that as totally different stuff, but it is still area.
Yep.
And then, of course, area under a graph, which is sort of pre-calculus stuff. But again, I see that as quite unrelated. But when they're doing area under a graph, they do need to know how to find the area of a rectangle, triangle, and a trapezium. So it all relates.
Got it.
Everything relates, obviously. So we'll look at some GCSE questions. These are all lovely questions from AQA.
Nice plug there. Love
Yep.
it.
And I mean, there's so much. There's so much interweaving in these questions. It's beautiful. I mean, you can see straight away this one's got ratio and area.
Nice.
But this one also is such a lovely, like anything that involves counting squares is just really conceptual, like what area is.
Yes.
And here all they're doing, they can count squares. They don't have to count squares, but, they're just going to write the 2 areas as a ratio and simplify it.
Nice.
So, there's 2 sort of straightforward skills there, but it's so it's kind of testing 2 different things. So they know what area is and can they simplify a ratio. The questions like this seem to, I would definitely do a lot of this kind of stuff with my students, because it's, to me, this is quite straightforward reasoning, but there is some reasoning going on here, because you're working backwards, aren't you? So you've been given the area, the rectangle should be straightforward, and any primary child should be able to do that. But we know that that's not quite so straightforward when it's a triangle, when they're
Tricky,
working
that triangle
backwards.
one there, isn't it? Like with the numbers, it's a good question. I like
You're right.
that one.
I think, it is tricky, isn't it? Because you're going to have a lot of them trying to do the 24 or doing 24 divided by 16. And so definitely not as straightforward. Yeah. Just, these sort of things, area of triangle and the forgetting to halve is something that comes up a lot. And, every time I mention area of triangle in front of a class, I say, people always forget to halve. I don't want anyone to forget that dividing by 2 thing, but they always do.
I told you that, didn't I? Years ago, when I first started diagnostic questions, one of my most kind of famous questions on there was an area of a rectangle, and the most common wrong answer wasn't like adding the sides, as you might imagine.
Yeah.
It was multiplying and halving. And the reasons given was that the kids have been told so much they're just halving everything, right? So you can imagine it kind of tips the other way, right?
because they're going to hear my voice ringing in their head.
Halve it.
Oh,
Yeah. So watch out for that.
Oh, dear. But you can see with this one, the one on the left is pretty straightforward because they're only given 2 lengths. So with that, they're going to multiply them together, and then the question is, will they remember to halve?
Yeah, and also, of course, you twist. You've got the non-kind of prototypical triangle.
Yeah.
You chuck an obtuse angle in there. And
Yeah, they're going to be confused with where the length is labelled, but also at the same time, they're going to say, well, I've only got 2 numbers anyway, so what, But then the one on the right, they are given 3 lengths, including one that is superfluous.
Nice.
And they have here's the work. This is like a common thing in GCSE, isn't it? Critique someone's answer.
Yeah, kids are bad at that, right? Generally.
Yeah, they are bad at that, and then also they get really hung up on like, that's always wrong. They say.
Yeah.
Like, has there ever been a GCSE question where the person is right? I'd be interested to check that. So they know there's going to be something wrong in there. But yeah, this one, it is the division by 2 that's a problem. But some of them will say. Some of them might say they should have used the 14, maybe.
That's
Don't
interesting.
know. Yeah.
Just on the one on the left as well, just a quick one on that. So, I love a bit of cognitive load theory and all that. So a reason that kids would forget to halve in that one might be that, firstly, a bit of attention's taken up by the fact the triangle looks a bit weird.
Yeah.
So straight away they're thinking that. Then they've got to give a lot of attention to how on earth you do 9 multiplied by 5.6, because they're thinking of like the decimal multiplication.
Yeah, I mean, I don't know if that was calculator or non-calculator, actually.
So chucking those 2 things, your attention's drained.
Yeah.
So you just simply have nothing left in the
I
tank to
see.
remember, I've got to. And it's always the final step of a process, whenever initial 2 steps are a bit weird that throws the kids. So
I see.
maybe it's
Interesting.
something to do with
Yeah,
that.
yeah, that is interesting.
That's literally the only interesting thing I've got to say. I've peaked in this video, but we'll see.
But if you look at that second one, again, the perpendicular height is drawn in a non-standard
Yeah,
position.
true.
So
Yes,
again, there's that.
yes.
Yeah, that. And I'll talk a bit in a minute, or later on in this session, I'm focusing a lot on perpendicular heights. Like that's one of the
Ooh,
things
now
that
we're
I think
talking.
is
Yep.
is quite an interesting thing. Got 2 more similar questions that are area related. So that one on the left, we've got a carpet measuring 8 by 6, and then we have this square, and you have to read the word square there.
Yep.
So that's important. So
Yep.
that's 2 by 2, and then it says show
that's
that
nice.
1/12 is covered by
good.
the rug, and it's a show that question, and so they're going to have to show some workings, and there's various ways they can do that. Like some of them, they might say, oh, well, the square is 4, and then if you multiply that by 12, you get
Nice.
40.
Yep.
But there's various ways of showing it. And the one on the right is similar, where you've got, again, a square that's 15 by 15, and then an x by x.
Yes.
And then they're telling you that that's 1/9, and you have to work out the value of x.
I mean, the thing I always take away from this is that it's so important kids get exposed to these kind of questions in the learning phase, right? Because what you don't want is that the kids do a load of kind of conventional area stuff, and they think they've nailed area, and then they get to an exam and a little weird thing like this, and all of a sudden they collapse. So these are, whilst they're assessment resources, these are great teaching resources.
Oh, definitely,
right?
yeah. I mean, this is all reasoning, isn't it? And we don't want we need to teach the facts and formulae, and we need to do the fluency practice, but then we need to expose our students to loads of stuff like this. But then also bearing in mind that when they get to the exam, it will be things they've never seen before.
Correct.
And that's the point in it, isn't it? This is one of my favourites from AQA because it's 3 topics. Can you see which 3 topics are in this question?
You're not allowed to ask me questions on this, right? Well, area, I'm assuming, is involved at some point.
Yes, because it says work out the area. yeah, that's the last bit.
Ratio would be in the mix.
Ratio. So can you see what the
Bit
other
of
topic
Pythag,
is?
maybe?
It is Pythagoras, yeah.
Yay,
And I
nice.
don't know if you, I see those numbers and I think Pythagorean triple.
Yeah.
So, we straight away know that that's, I'm going to embarrass myself, 15. Is that right? Yeah. Is that right?
Possibly.
I love the way that's got 3
Yeah,
topics,
it's
but
lovely,
also
that.
3 topics that students see a lot of.
Yes,
so
yes.
they tend to remember, you find students remember Pythagoras because it comes up so often, it's all over the place.
Yeah.
So I think this is actually quite accessible. I'm actually going to try. I'm teaching ratio at the moment, and my students are doing a lesson on this week on ratio and geometry, and they're going to have a go at this question.
It's a good
and
question.
I think they're all working it around a grade 4, but I think they'll be able to do this one. I like the interweaving of 3 topics in one question.
Just to go a bit deep on this thing, so you say using it with your kids.
Yeah.
What would you do? Kind of bang it on the board, give them a bit of time to think on their own first, bit of paired work? How are you actually going to use this in the classroom?
So many different ways. So I might do it as me modelling, but with questioning. That's the most likely way. So I'll probably have it on the board, and I'll ask for ideas.
Yep.
I might say, right, we want to work out the area. What dimensions do we need?
Nice.
And then someone might say, well, we need the height. Any ideas how we'd work that out? I might have a suggestion of Pythagoras. So I might do it through a bit of class discussion.
Yep.
Alternatively, it might be that I'm giving them some kind of ratio practice, and then this is on the board as a challenge. But then if I do have it on the board as a challenge and some of them have a go at it, then I will also go through it with the whole class. So I am really careful to make sure that my challenge questions aren't just for the people that finish quickly.
Of course.
So everyone then gets to have a go. Sometimes I'll model it just totally myself, but I think this is a really nice one for taking ideas from the class, get them involved. These are interesting. So these are pressure questions.
Ooh,
now,
flipping
pressure, new GCSE, they have to work out pressure.
Yep.
It's one of the compound measures, but the formula's provided. They might not be very familiar with this. I certainly don't do much of this with my students. When I'm teaching compound measures, I'm focusing on speed and density.
Yep.
But yeah, they are told the force, they work out the area, they then calculate the pressure using the formula.
Yeah.
The one on the right is perhaps a bit more interesting because it's a modelling question. As in, modelling is something that is meant to be assessed, or the idea of modelling is meant to run through GCSE and A-level, and particularly at A-level, this idea of we use mathematical models to solve problems. And here we want to work out the pressure applied by the iron, and Ralph has modelled it by saying that iron is approximately the shape of a triangle in a trapezium. So there's a lot going on.
There is a lot going on.
I think a lot of students will struggle with that question just from sort of. For a start, there's a picture of an iron on the left.
Yeah.
And then, don't need that. But also, just, it's a tricky question with lots of different elements, because they got to work out the area of a triangle. They got to work out and it's a triangle where, again, it's not your kind of standard right angle triangle. The area of a trapezium, and then they've got to use a formula.
I'm going to say, how many kids know what an iron is these days?
Oh, what? Yeah. Irons do still exist. It's not like the technology's been replaced, but they probably haven't used an iron.
Correct.
And they probably never looked at one from that direction.
Yeah, there you go.
So it's a really interesting question, but you can ignore the fact it's an iron and do the question. But it's the pressure thing that we mustn't forget that, we're teaching area. Where's it come up? Well, it comes up in compound measures.
And I'll tell you something that we should have said at the start as well, but we'll say it now. All these resources are going to be downloadable as a PowerPoint. So if you're looking at these questions thinking, flipping heck, I'd love to use that iron question.
Yeah, it's all there. Yeah. And all of these, like I've got these are from All About Maths from the past papers. Like all of these are AQA questions in there. There's the other thing that you can, when you look at these questions on All About Maths, you can see the examiner comments on how the students did, and you can see like the average mark on the question and stuff like that, which is really interesting. Just a couple more then. So trapeziums. Normally trapeziums cause a problem because no one ever remembers the formula. Unless their teachers taught them a little song, and often that works.
What's the song?
I don't know. I'm not singing. So. There is a song for the formula, and I don't really do that kind of thing. But I know that
I'd love to hear you do it. No. Do you know the words of it or anything?
No, I was about to try then. I'm not going. But I know that sometimes I'll say to students, "Who knows the area of trapezium?" and someone will say, "Sing the song." Yeah, so it must be fairly effective then if some of them remember it. So that's something people can look up for themselves. But this year, 2023 and last year, they're given the formula in the exam because of the COVID measures. But going forward, they might need to remember it. And we know that it's a hard formula to remember in a way because it's got this A and B in it, which they need to know what A and B means. But if you look at these two questions, they're not straightforward.
No,
so the one on the left, the two things I think are interesting about it is one, it's working backwards. But two, it's drawn in a different orientation to what we normally see a trapezium looking, in that the parallel sides are not horizontal.
And not marked on as well, right? You've got to kind of infer the parallel from the right angle.
Oh, yeah. Of course, yeah.
I like
so that's quite tricky. And then the one on the right, can you see what's tricky about that one?
You're going to have to use a bit of something else.
Yeah.
The trig.
Maybe. You're going to have to use right angle trigonometry to find the height. So both challenging questions. And if you ever have we have a class of students at our school who think they were being introduced to a surface area last week, year 9 students, like a top set, really smart. And the teacher started with a recap of area, and the students were like, "Why are you recapping area with us? We know this stuff. Why aren't we just doing the new stuff?" Now, given these questions, and there's challenge. There's challenge because it's reasoning, there's interweaving, there's all sorts going on here. So we mustn't ever assume that area is just too easy, skip it. There's plenty of challenge in area.
Just a quick one as well. I talk about this in my book, Tips for Teachers, available in all good and evil bookstores. I saw a lesson on area of a trapezium. And the worked example was just kind of prototypical isosceles trapezium.
Right.
Normal orientation. Kids nailed it. Follow-up example, same orientation, everything the same. Question 1 on the worksheet, everything the same. Question 2, it's turn round. There's no parallel sides marked on. Kids didn't have a clue what's going on. I'm obsessed with making sure in worked examples you use non-prototypical examples. The more I see lessons kind of fall apart when you stick to the conventional.
And actually, it's really interesting because I did a lesson observation last week where a teacher, she was doing linear graphs and finding x-intercepts. And so she modelled a couple of examples that were very straightforward. So it was y equals mx plus c, put a 0 for y. And then she showed a less straightforward one, which was something like 2x plus 3y equals 18. And then that took quite a while to model. And then the task went straight into the easier ones. And because they just watched quite a long bit of modelling on the difficult one, they were just really confused. So that's when I said to her, well, have you read Craig Barton's book? Because example problem pairs would have worked better there.
Good.
So like it would have been a good idea to do here's like the straightforward example, you do one, another one, you do one, and then look at the sort of non-standard ones, and then just doing it, because then they're not so overwhelmed when they start the task, because it's, they've got some examples written down, they've practiced it like step by step. So it's you're right, you've got to be careful with how the task relates to what you've modelled, and are you showing these non-standard examples, because they're not these aren't non-examples, these are boundary examples and things like that. Nice. And then one final bit from AQA, and this is a really nice examples of questions where it's interweaving with coordinates.
Oh, lovely.
Yeah, so they're a little bit different. So the one on the left is saying that we've got two coordinates, so we can just mark them straight away. So we've got A and B, you put them on there, and then you're told C is on the line, Y equals 4.
Yeah, that's good.
And then so I mean, it's a lovely question.
It's really
nice. How the height of the triangle, but you could put that anywhere and it would be the same area.
I've not seen that one before.
Isn't that nice?
You could build a lesson around that question.
Yeah.
Hey, and bit of modelling, fire up a bit of GeoGebra and stuff.
Yeah.
That is
it's great, isn't it?
lovely.
Yeah, wherever we put that
Whoa.
point. You could put it really far away and it would still be the same area. You could have a really obscure looking triangle.
Lovely.
Not
yeah,
the word, but
love that one.
The one on the right, they're told the area is 28. And they can just find any coordinates for A, B, and C that give an area of 28. Now, I've given this one to students, and my students did really struggle with this. Because the way I see it is, because you might originally think, if you kind of, it's quite advanced to already think, well, I might want those two to be, say, 7 apart, and then you might think that C to be 4 away, but that's wrong because it's a triangle.
Yes,
so you need like 7 and an 8 or something like that. It doesn't have to be 7 and 8.
Yeah.
And then you could say, but then how do I make A and B 7 apart? One's got to be negative. Isn't it nice?
Hey, I'll tell you what, though, as well, with that, if you really wanted to have a laugh with that one on the right, my classic quadrant kind of learning generative examples. So you could say, come up with an example where it's 28.
Yeah.
Come up with another example of coordinates where it's 28.
Yeah.
What's the most interesting trio of coordinates you come up with? And then can you come up with a trio of coordinates that somebody might think comes up with a triangle of area of 28, but it actually doesn't? That'd be nice, wouldn't it?
Yeah, that's really nice. Yeah, because you could make the A and B like a unit apart, and then you could have a really long C. And you could even use some surds or something in there. There's all sorts of things you could use. Yeah, nice, really lovely.
Yeah, love that.
So that's a load of GCSE stuff. I'll just mention A-level because we should understand the full curriculum, even if we're not teaching A-level. Does area come up at A-level? Of course it does. It's everywhere because it's so fundamental in maths. It comes up in trigonometry. It comes up in integration. It comes up in trapezium rule, coordinate geometry when you're dealing with, say, circles, histograms, like areas everywhere. One of the most fundamental concepts that we teach.
And that's, again, like you say, even if you don't teach A-level, this idea of the maths we're studying today, this is where it's come from, and now this is where it's going. It's so important.
I mean, I think it's one of the things that's changed so much in my narrative of lessons now. In my lessons, I'm constantly referring to what they've done previously. Say, right, do you remember in year 8 you did index laws? And I'll mention it all the time. But then I also talk a lot about where it's going. And I'll really say, important. Like particularly at GCSE, but in fact, with even sometimes I find myself talking to Key Stage 3 classes about when you do A-level, this is going to be, like I'll say, right, we're doing index laws, and when we do A-level, this is going to give you access to calculus. And I say that kind of thing all the time now. I never used to do that. I should also mention area coming up all over the place in other subjects. Now, these, I'm not going to claim to know a lot about other curriculums. I think that first question from DT, I'm like, am I missing something? Because it's talking about finding the area of an A4 sheet of paper. And then it's multiple choice. Now, as a mathematician, when I look at the two numbers you're multiplying together, I know the answer ends in a 0, and I don't even have to work anything out there. As that's how a mathematician looks at that.
And as someone who loves a diagnostic question like I do, I'd be interested in thinking where those wrong, what those wrong answers are revealing.
I wonder if one of them's a perimeter. Like, could it be? No, it can't be.
I don't think so.
Where have they come up with those numbers? Oh, we have to look at that. Interesting. And then the other one, now there might be more complex area on science, and I know they do area under a curve, but a very simple area question in a science exam. So we can see that, area is coming up other places, but I said probably not in particularly complicated ways.
Yep.
And the other place area comes up is in real life. Have you seen this?
I did see it.
It's nice, isn't it? So this is this is from a review on Amazon where someone has bought a box of very nice wooden floor tiles, and it says it covers 10 square feet, and they have a bit of whatever that is, patio, whatever that is, 10 by 10. So they have assumed that that will cover that ground because it's 10 by 10, and we know that obviously that is 100 square feet. And it's just, really how frustrating to people that make that to get 1-star review for someone who can't do basic maths. Yes, area is definitely. I don't like to tell students things are going to come up in real life because most of that is not true, and that's not, in my mind, we're not teaching maths because they're going to be using it every day. We teach it because it's interesting and it's fascinating and it's enjoyable. But area, genuinely, if you are doing DIY, is something that might be relevant. And it was in this case.
And the kids love anything like that. Whip that on the board.
Oh, that's hilarious. Yeah. Right, and then I just want to mention one more old textbook.
What year are we going back to here?
So this is
61?
1961.
Okay.
Although first published in 33. This has got a real nice old textbook feel to it. It's the kind of hardback. It's really, I love these books. So this is the Essentials of School Geometry. And when you look at, it's hard to find old geometry books that aren't just solid Euclid and like really, really heavy. This one's a bit more modern, so it's not too bad. This is after the MA, the Mathematical Association, got involved in reforming the curriculum. So now this looks a bit more like our current curriculum. But if you go back to 1800s, the geometry is very, very heavy. And if you look at what they were doing in this book back in the 30s, and then you can see really similar stuff. Not the same sequencing that we would necessarily do.
Interesting. Yeah,
so we've got area rectangle, then parallelograms and triangles, which they put hand in hand, and they kind of should go hand in hand, really. And then constructions, and then quadrilaterals and trapeziums, and then some more constructions, and then Pythagoras and loci, and that to them is one big sequence, which is quite different, I think, to how most of us would do it, just in terms of ordering, like, putting those constructions in there. Constructions much less relevant these days.
3 lessons on a year 7 scheme of work, get through all of that.
Yeah, and it's interesting, isn't it, that actually I think a lot of people give area, like I give area in year 7 2 weeks, and a lot of people give an area 1 or 2 lessons because they're saying we've done it before and they're just skipping it. Yeah. And just I like these definitions here. The area of a figure is the amount of surface contained within its bounding lines. But you can see that our language has changed slightly there. I don't say bounding lines. The unit of area is the area of a square on a side of unit length. The square inch is a square drawn on a side of 1 inch in length. See, our language has changed, but the concepts are the same.
That's good.
And then another thing worth looking at is how they teach it in Japan.
Oh, nice.
Japanese textbook is so nice.
Yes.
And this is very primary level. They teach things at a much younger age, and they go into greater depth at younger ages there. But this is their very first introduction to the concept of area, and the idea is which has more space. So they're looking at 2 different rooms with different shapes. But you can see if you look at the 2 rooms at the top, they are the same number. They're the same space, different shapes. And then again, you've got the 2 different shapes at the bottom. And the question is, do they have the same area?
There's so much just in those 2 images.
Lovely.
There,
yeah.
Right?
They know how to do conceptual development in Japanese textbooks. It's really nice. They're very different to our textbooks, which are, say, 2 examples and a short exercise. Like, it's all about conceptual development. I like this one as well. I mean, the language is very advanced, and I wonder if that is the translation. But for a primary child, we subdivided the territories into squares. It's quite advanced. And they're saying how many 1 centimetre squares are in each territory. So that's a counting exercise like our students do in year 4. Which territory has the most space, and by how much is one larger than the other. Now, that's straightforward stuff, but it's just really nicely displayed and really nice about understanding what area is.
Yeah, it's good.
And they go on. I love this. I just love the way they do. Even if you look at that where it says 1 centimetre square, and you can see 1 square centimetre, you can see the formation of the letters is drawn out. This is for young children.
No, I haven't seen that.
And they're showing how you draw the C in the end, because the children are that young. But I love the way they define. I love that picture with it on the fingertip to give it some context of how big a square centimetre is, like to give it some, you've got something to compare it to. But
lovely, that.
Isn't it nice? But I'll just show you a couple more examples from the Japanese text. But this is from book 4B. They start with the concept of what area is. Then they look at areas of rectangles, then areas of L shapes, and then they start looking at different units, because everything originally is square centimetres. They look at metre squared, hectares, and square kilometres. And this is a typical exercise. Look at the ramping up in difficulty here. This is for very young children. So the first one is just find the areas of these rectangles and squares. But look at even question in that first bit, part 4, a square with perimeter 12, very young children. And then we're bending this wire, and what does the area end up as? And then straight onto these compound shapes and problem solving and reasoning. Like very, very quick ramping up there. I don't think.
What age would this book be for?
I don't. Yeah, it's book 4B, so I assume it's year 4, but I don't know what their year 4 is. And then I won't go into book 5B, but in book 5B it says it's then straight into parallelograms, triangles, various quadrilaterals, and then the relationship between height and area. So that's working backwards. I mean, look at that. It's just it's a shame that we don't have access to these.
And it's also a shame, we've said this before, right? It's a shame we don't have like a really good national textbook or whatever that's been, because these examples have obviously, they've been refined over years, if not decades, to get the best examples and stuff.
Yeah, absolutely. Yeah, there's a lot of expertise.
One day. Oh, here we
Right,
go.
so we're going to have a look at some resources, how to go into depth, how to challenge students, but we're going to mainly focus, because there's a lot to say here. I'm going to mainly focus on 2 areas. So because I only have time to look at 2 areas, I'm going to start with, do you want my animation there? It's clever, isn't it?
I've never seen that one before. Flipping heck. Okay, you're right.
Area,
Yeah.
I'm glad you like it.
Jeez.
Area with reasoning with area, and that is
Okay.
like making sure they understand the concept. So we'll look
Yep.
at that, and then here it comes
Here it
again.
comes again. God. Wow.
Triangle misconceptions.
Okay.
So again, I can't talk about everything. I could go on all day.
Jeez.
Yeah.
Oh, very right.
Do you like-
God,
you
you've
like
really
this
gone
slide,
to
don't
town
you?
with this.
Yeah.
You could do PowerPoint in depth for another
Okay,
session.
couldn't I?
It's good. Very
Yeah,
good.
I should do
Very
that.
good.
Right, so we'll start with some reasoning with the concept of area. Now, I don't know. Have you seen this Smile resource? Smile resources
I've
have been
only
around for a long
seen it.
time.
I only seen it because you showed
Okay.
it. Yeah, I love a bit of Smile.
Yeah, I mean, they're available on STEM Centre.
Yep.
They are scanned in, so but they're very usable, even though they've
It's
been
hard to
scanned
find
in.
the thing you want, though, right? That's
Yeah,
the thing.
because they're not brilliantly indexed, because they are old. It's not, you can search on STEM Centre for area resources and they will come up, but they're just you have to kind of know your resources really well to
Yes,
find this kind of
yeah.
thing.
It's good,
Now,
that.
if you look at this, you've got unusually shaped polygon. You
Yep.
know, I don't even know what that is. What is that? 1, 2, 3, 4. It's a pentagon, is
Yep.
it? I'm always careful with that. When I talk to students, like, say I have a shape on the board, if it's like an L shape, I'll say, right, so we call this an L shape, but let's just check. Oh, yeah, it's a hexagon.
Yeah,
and I will
that's
always
good.
say, this is the actual word for it. Look, and I'll make sure they see me counting the sides. This is a
Nice,
hexagon. Like, we should say that whatever shape we're looking at. We have 2 ways of finding the area. So we could split it into different
good.
shapes. Or we could, or you could talk to them about, can you count the shapes? And you say, but hold on, what about those little bits where we can't tell how much, what fraction it is?
Yeah.
So actually, it's better not to count the squares. It's better to split it and say, well, say for example, on the left, shape 2 is a triangle, so we can do half base times height for that. So there's a lot of calculating and working out. But then on the right, perhaps it's quicker to box it in and just do. And that's a huge bit of reasoning for them to understand. If you want to work out the area of something, you can always take away the bits you don't want. That comes up a lot.
And it's not intuitive to me to do that boxing it in until I saw you.
Yeah,
doing it. But
I don't
love
think
it.
I would have thought to do that.
I love a bit of boxing in. It's
Yes,
good,
and it turns out that is a very common method, the boxing in thing. But then that resource gives them some to try for themselves. So they'll either box in or they split it. And, I like to say to students, choose whichever. I've shown you 2 methods, choose the one you prefer.
Tell you what, like E and F are tricky there, right?
Oh, you know what? I have made the mistake of not giving this task enough time in the past. Like, this takes a while. Yeah. And the thing is,
That's good,
this is
that.
where you're over year 7
Wow.
class and you think, is this too easy for them? No.
Definitely not. Definitely not.
But then it turns out that boxing in is actually a word, like a
okay.
term. Like, I haven't just used that. Like, that is actually officially what it has been called for many years.
Jeez.
Haling's books are incredible.
Yep.
Some of them are quite hard to get hold of. They're quite expensive. I have the full set of Haling's books. I'm a big fan of them. Normally they've been donated to me. So when people are clearing out their cupboards in maths departments, they find
okay.
old
Give you
Haling's books.
Haling's.
Yeah, so like people normally have them lying around. They're from the 80s. This one's from the book Area and Volume. Haling's books went into depth, so you had a whole textbook on Area and Volume. They're quite thin books, but and you can see that they actually have a whole section on the boxing in method, and it says it can be used to find the area of an awkward shape by enclosing it in a rectangle or square and then subtracting the unwanted pieces. And the subtracting the unwanted pieces comes up in loads of other bits of maths, like if you're doing stuff with circles, like complicated shapes. Often you're subtracting bits you don't want. So this was the first time I'd actually seen a name for it, like boxing in. It's quite nice.
And anything where you've 2 different ways of arriving at the same answer is always a useful thing to do with
Absolutely.
kids.
And that's something teachers have to be careful of. So say, for example, we had something very similar to... It was something in a warm-up where it was some kind of compound shape. I think it might have been like an L shape or something. And I'd taken an answer from a student on how to work it out, and they'd done it by splitting it into 2 parts, which is probably what I would have done in an L shape. And then I said, right, did anyone do it a different way? Because I was expecting them to say they'd split it, say horizontally instead of vertically. And then a student put up their hand and said that they'd done the boxing in. So they'd worked out the whole rectangle and taken out the bit they didn't need. And it just, you have to be careful not to miss that, because if you say, just go through the one method and then you move on. You've got some students sitting there feeling that they want some validation of their method, and they're thinking, oh, I did it differently, but the teacher just said, and I've seen students mark things wrong when it's a different method, when their way was perfectly valid. So it's so important to just, even if you just say, some of you might have done it differently, but if you arrived at the correct answer, then your method is great. So, don't worry if yours doesn't match how I've done it. So it's important that they feel like they don't have to mark things wrong if their method doesn't match.
That's really, love it.
Right, so we have similar resources. Again, a different one from Smile, the one on the left, where, again, they're calculating the areas by either boxing in or by splitting. And then they design 3 of their own polygons and finding their own areas. And then a similar one from Don Stewart, but lovely. He calls it area by subtraction, which I really like. So again, everyone's got this kind of idea of how do we find these areas, but it's all about the concept, isn't it? We want to know how much space is taken up by the area. We want to know how many squares.
I don't think we've ever done a Topics in Depth without featuring one of Don's resources either.
Yeah, I know. And like, it's if you're looking at something if you're looking for challenge, look on Don's website. If you're looking for something interesting, then that's the place to go, isn't it? Any CTM resources, they're lovely. There's so many good things in there, and I just need to take more time to go through them. And I need to remember to use them in my lessons because they're quite new.
I don't think these are used enough, And I can only say this, so I'm lucky I get to visit loads and loads of schools.
Yeah.
I don't think I certainly haven't seen these this academic year being used at all. And it's just because there's so much stuff out there for maths teachers, right?
Yeah.
And it's knowing what to pick. But these are gold.
The thing is, if you're an experienced teacher and a whole load of new resources come out, then, I reuse lessons from previous years. And it's it takes a bit of effort to say what else is out there that might benefit my students. This one is lovely on the concept of area. Like, which of these shapes is bigger and what do we mean by bigger? So their first question is, which one do you think is the biggest?
Yep.
Does putting a grid on help? Like, they're really nice design, clutter-free slides. Yep. There's no nonsense on these slides. They're just really, really easy for students to access. In which way is it bigger? So they might talk about perimeter, they might talk about area. Nice. I don't know, just looking at, do they all have the same area on there? Probably. I think maybe they do. No, maybe not. I think they do. Can you create shapes with the same area? See, I can't tell by glancing at it. I'd have to sort of quickly count them. I think they do all have the same area. I think they're all 5, aren't they? Yeah. And then, so just really nice in terms of what area is.
Yeah, lovely. Love that.
But then that leads us on to, so this is MathsPad.
You love a bit of MathsPad as well.
I literally every day I use MathsPad. There's not a single day that I am
Saturday
not using MathsPad.
Maybe even at home.
I plan on Saturday and Sunday, unfortunately. So yes, I'm always on the website.
That's good.
Yeah, it's nice, isn't it? Because this is fractions interweaved with area.
Yes.
They have to understand the concept of area to be able to do this. But look at the challenge there. Like it really look at the last one there. Like there's a lot of thinking, and they have to know how to work with areas of triangles to be able to do this. And there's a lot of understanding going on. But then that leads them on to the really complex problems. Like this is the classic Solve My Maths Ed Southall's puzzle. It went viral, and it was find the area of the pink triangle.
And I'm crap at these,
I'm not the best at sitting down and having a go because you have to really try, and so you have to give it some time. I think sometimes mathematicians just assume they'll be able to do it instantly.
Yeah, I think you're right.
And also sometimes, particularly if you're seeing them on social media, people are answering in the replies, which they shouldn't do, because as soon as I see an answer, I won't try the question.
But this is like, just on a kind of pedagogical point, like, I don't know if you found the same, Joe, but like using the resource on the right, using it effectively in classes is tricky, right? Because what you want, the worst way to use it, well, I think there's 2 terrible ways to use it. Way one is you bang it up on the board, you give no support whatsoever. Some kids are like, this is the worst experience of my life trying to do this. But the other worst way of doing it is you bang this on the board and then you just tell the kids how to do it. And you think you're doing problem solving. So it's finding that balance, isn't it? You want to let them struggle for a bit and then perhaps get a bit of information from them. It's hard, isn't it?
Yeah, sometimes I would try and find a couple of similar questions to model or something. Yeah, there's all different ways, but you're absolutely right. This isn't just hey everyone, here's today's lesson, get going. They're going to hate it. They're going to really struggle. And also the Solve My Maths problem, I'm not suggesting that we're giving that to our Year 7 students, but if we have students who we're saying, we've got a top set and we're saying, oh, I don't need to do area with them. Like, really? Have you tried like the really hard stuff? Because there's plenty of it. Like, we shouldn't be skipping stuff when we could go into depth and challenge like that.
Of course.
But this is an example of one where I have I've had students get stuck, and their resilience is an issue on this one.
I've not used this for years.
Yeah,
You've
it's
reminded
Sanders
me of
unit,
this.
so it's classic. Yeah,
It's classic. Jinx.
it's and it's a lovely problem
That's
in that
good.
I think it might even be in their percentages. I can't remember where it comes up, but I feel like I've used this in 2 topics. I've used it when teaching percentages on fractions and the conversion between fractions and percentages, and I've also used it on area, because it's not necessary. Like, people don't see this as an area problem, but the whole problem's about area.
I've forgotten about this one.
It's lovely, isn't it? You know what they do? Like, they're normally they A, no problem, and then B and C they're probably
They're
fine
all right,
with, and then they'll put up their hand and say can't do E. And the thing is, they should be able to do F, no problem. But even that, I mean, you know, it's developing those mathematician skills. Draw some lines on the diagram, like draw that horizontal across. You know.
Choose some good numbers to use. So much good stuff.
Yeah, and it's actually the skill of drawing lines on diagrams is absolutely vital. And then when they get through to A level, if they've developed that skill, they're a mathematician that knows how to solve problems.
Lovely. That.
So yeah, I mean, this is again one of those things where leave longer than you think you'll need. Like this has definitely taken over most of a lesson before.
But like this wouldn't be out of place in certainly a year 6 scheme of work or a year 9 scheme of work, right?
Oh yeah,
like
definitely. Yeah. Lovely reasoning in this one,
stuff.
and the equivalence between fractions and percentages, all sorts going on.
I mean, I think you've peaked there. I think it's stopping there, because what's getting better than that? That is
I think anything from, I think a lot of newer teachers just don't know Standards Unit, and they are beautiful resources. You've got them on your website, haven't you?
I have.
Yeah. And there's just so much in them from a reasoning point of view. Like, reasoning should be in all of our lessons. And we've got to be careful not to say, oh, I've reminded students how to work out the over triangle, they've tried some practice questions, let's move on. Like, use some reasoning, do some lovely maths with them. Now this is totally different.
Oh, yes.
Are you familiar with Pick's theorem?
Yeah, I am. I don't know how, but yeah, I am.
Back in the day when everyone used to do these investigations, because you used to teach back in the day, so you've probably done this kind of thing. Because it used to be very fashionable to do this kind of thing. So this is back in the day, not being 1899 though. Right. So this is not when you were teaching, but you definitely would have done a lot of investigation style things, I assume. And this is one of those classics.
It's weird, isn't it? I remember thinking that time was a bit weird.
Yeah, I tell you what, I'm not a big fan of doing this with students, but I am a fan of teachers knowing about it because it's interesting. But not doing it with students so much because it's really complex, and it's too complex for the maths that our students can do.
Yeah, it
like,
is.
some people will disagree with me on that, but let me just explain how it works then. So if you have a shape drawn on a grid, you can work out the area of that shape without any calculation of using, like, you know, half base times height or whatever, but of just counting the in this case the points or the dots around the perimeter. So that's P. And then the points on the interior that aren't on the perimeter, so call them I. And then there's this formula, which is you take the interior points and you add half the exterior points and subtract 1, and it gives you the area. Now, I don't think anyone would even necessarily spot that pattern, even if they did loads of these.
Well, there's 2 things I don't like about it. I mean, I'm like you. I find it very, very interesting. There's 2 things I don't like about it. The pattern's not obvious. And that's not the worst thing in the world. But it's the P perimeter thing. Like, it's misconception central, right? Because your perimeter is just you know, perimeter of that triangle. It couldn't be it couldn't be further away from 8 if it tried.
Yeah, that's what you mean. Yeah, because the P is for the points. Yeah, you're right.
It's just a bit dodgy, that's
but so there is a whole enriched thing on this. But you can see what they're doing is they're asking students to kind of draw a load of them, try and spot the pattern. Now, they're not asking them to understand where it comes from because it's really, really complex.
Of course.
So I'm not sure there's value in it. I know that, again, like I said, this was very fashionable maybe 15 years ago to spend a lot of time on these sorts of things. Pattern spotting, definitely worth doing, but I think it's a really hard pattern to spot. Like, you know, so especially, you know, no one's going to look at the numbers and say, oh yeah, I can see what's happening here, because it's not intuitive at all. But I think the only interesting thing about it, or the thing I find interesting, is it's like, what? You can find the area doing that?
Yeah,
like,
I'm with you there.
But I thought that's the sort of thing where perhaps if you're running maths enrichment, that might be useful. But it's not something I'm choosing to do in lessons.
Yeah, it'd be interesting, teachers watching this, what they think of this. I think it'll split the crowd, this one. This wouldn't be, whereas I definitely take the standards unit. I think every teacher needs to expose every kid to this. Picky, I'm not. Anyway.
So that's
Now we're
concepts, and then
talking.
the
Now we're
second thing I want to
talking.
talk about. Yeah, I mean, you know a lot about misconceptions from your
I do.
diagnostic questions, and I'm going to show you one of your diagnostic questions. I don't know
Okay.
if it's one you wrote, but it's one you'll be familiar with. So there you
Yeah.
go.
Oh, I am. You know what? I don't like this question.
Why
Jo.
don't you like it?
Right. I think it's good in kind of addressing the misconceptions, but it's like an impossible triangle. It doesn't fit with Pythagoras. Do you know what I mean?
Oh,
Yeah, do you know
terrible.
what I mean? I know. So now I use this almost as a little kind of thing afterwards. So I'll use
How
it as a
interesting.
kind of let's get the answer, let's get the misconceptions.
Yeah, of
But then
course.
with the kids who've done Pythagoras, I'll say, notice anything
Yeah.
about this? Yeah,
That's
it's
so
bad,
interesting. Yeah, I didn't notice that, and
Yeah,
actually, yeah, I will never use this.
hey? But there are equivalent ones on
Yeah.
the
So
side. but
imagine
the
this different one,
Yeah,
and
yeah.
So the idea is okay. So we've got an isosceles triangle. We want to work out the area, and you've got the four options
Yeah.
where you've got the kind of classic things. So our 6 times 7 divided by 2, which we know is the correct answer. We've got multiply the three numbers together.
Yeah,
Sometimes
classic.
people think area, multiply numbers, just yeah.
Correct.
Then you've got the selection of the wrong height.
Correct.
And then you've got what I thought was forgetting to divide by 2.
Yeah.
But then there's this really interesting thing, because obviously you get students to write what it is that they've and
Yep.
and this one just fascinated me, because I have seen students do with this kind of thinking before. This one student says, you don't have to halve this sum, as the triangle is made of 2 right-angled triangles. So he or she is choosing not to divide by 2, because they're seeing it as, well, I've got a 6 by 7 divided by 2 and another 6 by 7 divided by 2. Isn't that interesting?
It is.
Yeah, so like I just assume it's a forgetting thing, and this was a conscious decision not to divide.
I'm biased, obviously, because like it's my website, but the reading the reasons for the wrong answers is fascinating. It's such a useful thing. And again, I'll just bang on for 30 seconds about this. But if I was using this question in class, my mantra with diagnostic questions is the thinking doesn't need to stop once you've got the correct answer.
Yeah.
So let's say you put this question on the board, and the vast majority of your kids correctly identify that A is the correct answer.
Yeah.
You can then quite easily say to the kids, okay, here's a challenge for you. So challenge number 1, why do you think somebody might think D is the correct answer? And how would you help them realise it's not?
Yeah.
And then challenge number 2, can you change the question as little as possible to make C the correct answer?
Oh, interesting.
And it just
Okay.
means that you've always got some extra mileage you
definitely.
can get out of
Well,
the
yeah, I mean,
questions.
I normally, when I'm using one of your diagnostic questions in class, I will go through and say, I will choose a child to explain each answer. Like, why has this been put as an option?
Yeah, good.
And you do get lovely, like, really and often they'll say something which is not what I had in mind. I was doing one the other day where they kept coming up with these reads. I think it was an expanding bracket one, and I think they had just like say they'd forgotten to do the term multiplied by the second term in the bracket, but they had thought it was other things going on, or I don't know. It was just something really interesting where they said things I wasn't thinking of. It just goes to show that they don't need to read my mind.
No.
Like everything they say is just as valid as what I think.
Exactly.
So I think always lovely discussions with these. Like they're always worth doing. This was from an American blog, Mrs. E teaches maths.com. And what I thought was interesting about this, it says, when she teaches geometry, she wrongly assumes that students remember what they have previously learned.
Fair play.
I know students learn how to find the area of parallelograms and triangles in middle school, so I assume I don't need to teach it in as much in depth. Wrong. I have found students often make mistakes when finding the height of a parallelogram or triangle. Now, I like to look at things from other countries where you just shows they're having the exact same issues we are. And in fact, if you look back through old textbooks, they have the exact same issues for hundreds of years. Like these aren't new problems, and they aren't a problem with the way we teach. It is just a common thing that students struggle with. So she has then got a whole load of resources to do with like where they're highlighting to identify perpendicular sides and stuff like that. So she's writing a whole blog post about how she addresses it. But I think the interesting thing there is just how it's a universal issue.
Yes.
This is her old textbook. This is the one I showed earlier. So this is from like the 30s to the 60s. And notice there's a slight change, a slight difference in language here to what we're used to seeing.
Yes, yeah.
Because they're talking about the altitude or the height. Now, altitude, the altitude of a triangle is the perpendicular height. in England, we are not using that term,
No,
but
I've never
I
used that.
believe in Scotland, they, at least some teachers in Scotland do, because when I presented this last, a Scottish teacher said to me at the end, we all say altitude. I don't know if all Scottish teachers say altitude,
And it's
but
what, the perpendicular.
perpendicular height, yeah. So I would call it
Wow.
perpendicular height.
Yes.
But they've got an
I
actual word
guess
for it.
because height's dodgy, isn't it? So I guess.
Yeah, we don't use height.
So
yeah,
maybe altitude.
Yeah.
Okay, maybe.
But
I'll
I
start
mean, so
tripping
I'm not
into it.
suggesting I'll start calling it altitude, but it's nice to see that there is actually a word for that, and it was used in old textbooks. And at some point, we've obviously just stopped using it.
And they'd use. Could the base be an altitude as well? Like, would they be happy enough with it? Is it just? Is there always two altitudes to work out the area?
Yeah, good question. I don't know how they define altitude, because you're right. They're both
Interesting, isn't
perpendicular
it?
to each other. So
You need to look that up. You look that up.
Have you seen this from the formula sheet? This is
It's weird. I'd never seen this before
So this
in my
is the
lifetime.
2023 and 2022 formula sheet provided, DFE provided, and it's just an interesting phrase.
And it's not the worst thing you've ever heard in your life.
No, I
perpendicular
mean,
separation.
yeah.
It's weird though.
It's just funny to use a phrase that no one has ever used in the history of maths teaching. Like, I don't know why they came up with it, but yes, it is a perpendicular separation.
It's good. I like it.
But why not call it perpendicular height? I mean, it's literally the letter H, and also no one would have said this word ever. But
Someone's come up with that, haven't they? And it's not catching on.
No,
it's a shame.
No. But you can see, like, this is really nice. Parallelograms and triangles situated, as in the figures below, are said to be between the same parallels.
Nice.
Which again is something I've never heard it explained. And if they're between the same parallels, they have the same height.
Lovely diagram, that, isn't it?
Yeah, it is nice, isn't it? And you can sort of, they don't have the same area because their bases are different. So like if you look at the two triangles there, the heights are the same, but the bases are different.
It's interesting, again, just going back to that same point, this use of base and height, it is potentially problematic. It's so common, isn't it? That maybe it's okay. I don't know, as long as you emphasise, you can always turn something around.
Yeah,
So
I mean, I looked into the
tricky.
base thing. I can't remember what that was. For some reason, there was a question about the word base. Oh, I think it was maybe someone was asking about isosceles triangles, and we say the base angles are equal.
Yes.
And I looked a lot into the history of the word base and what we mean by that. And yeah, it's interesting, isn't it? It's the only reason it doesn't sit well with us is the word base suggests bottom, and it doesn't need to be at the bottom.
Yeah,
so that's the reason that it seems like not quite the right word we want to use. The base being at the top. I've got a teacher at my school, and she's so funny. She says with isosceles triangles, she talks about the equal angles being like your feet. And actually, that's a really nice way of looking at it, because isosceles, I believe it means equal legs. So she talks about isosceles means equal legs, and the equal angles are your feet. And she says, even if you lie on the floor with your legs in the air, the equal angles are then at the ends of your legs.
Is she a visual of that coming up on the screen?
I know, and I assume she doesn't actually lie on the floor and put her legs in the air, but it's quite a nice. I get what she means. Like, just picturing that the equal angles of your feet means that they'll always remember it's at the end of the legs.
I like that.
But so this is a Japanese primary textbook, and you can see they're using that idea of we've got a load of parallelograms that have the same base, and because they've got the same height, they all have the same area, even though they look different.
Yeah, nice.
And then this is Haling's from the 80s, same idea there. I've got a load of parallelograms with the same base and the same height, and therefore they all have the same area.
And again, we've got the advantage these days that to obviously show that the static image is powerful, but then
we can use dynamic. Yeah, absolutely.
So powerful.
I mean, this is, I think, the best diagram I've seen of it. This is from Paul Rowlandson on
We love a
pondering
bit of
planning.
Paul
Yeah,
Rowlandson.
he's got a great blog post about parallelograms, and he's saying about how these have the same base, and I love the way he's used the ruler at the bottom, so you can see that, and they have the same height. So even though it doesn't look like they have the same area, they do, and it's such a good talking point with students.
The fact that the measurements have been taken off, that is such a powerful image.
So you can talk about how you mustn't ever multiply the base by the slant height, because that would give you different areas. It's a really nice image.
Yep, love that.
And NECTM have a great exercise, just practicing the idea of base times perpendicular height, which students need a lot of practice of that. So in this case, it's you mark on the base and the perpendicular height. The obvious one there is in because it's a right angle triangle, triangle 2. Can you mark more than one different pair?
Clever.
So if you think about triangle 1, my original idea is to draw, say, the base is along the top, and the perpendicular height comes straight down the middle. But of course, I could have used the base as the left-hand side and the perpendicular height.
Good.
So that's a nice thinking point, and then they give you one where your perpendicular height will be on the outside. So that's lovely from any CTM again. So here's an example from MathsPad where it's quite straightforward. They're just identifying the perpendicular sides. which is really like a helpful skill, like an entry point to, right, we're doing areas of triangles. Let's make sure we understand what the word perpendicular means.
I'll tell you just on this one. So, I love a bit of kind of atomization.
Yeah.
So if you take calculating the area of a triangle, some teachers might think, oh, that's just one process. You teach the formula and so on. But if you break it down into its little sub-steps, this is such a key part of it. Like, if you can't do this bit, you're a bit screwed with the rest of it.
Absolutely,
and what you don't want to be doing is thinking hard about this, and thinking hard about substituting into the formula, and thinking hard about what units to use, and thinking about, you want to make sure the kids are fluent on each of the steps before you kind of integrate them together. So you're not spending more than 5 minutes doing this, right?
Yeah.
But it's going to make a world of difference when you then integrate this into the kind of more complex process. I love that.
And this could be a worksheet they complete, or it could be a cold call, like it's on the board, and there's all sorts of ways you can use this.
Mini whiteboard, anything.
Yeah, definitely.
Yeah, love it.
Another one from NECTM. I like this because it's like, so do you have enough information to calculate the area, the perimeter, both or neither? And I think that's so lovely.
Powerful.
Yeah, because in some cases, you might be able to get the perimeter if you use a bit of Pythagoras, for example. Like if you look at maybe F. No. Yeah.
Yeah.
I don't have to think about it. Or like, for example, on question, C, definitely. Like with Pythagoras, you can get the perimeter, but not just using, not just by glancing at it.
Yes.
Some of them you can get the area. Really interesting. What other information would you need? Is there more than one way to do it?
Clever.
Like, lots of deep thinking from these lovely NECTM tasks. And one more NECTM task. Gaynor says that the area of this parallelogram is found by working out 10 times 6. But Ollie does it by doing 7.5 times 8. And this, I think it's quite advanced thinking.
It is.
I never thought about this before I was a teacher, and how you could use either base as long as you use a perpendicular. Really interesting.
I'll just tell you a little fact on this. You ready for this? So this is hot off the press, right? So first thing to say is, you can imagine giving this to a load of kids and they're like, I don't know, because they're not used to verbally explaining things in maths and reasoning and so on. So I was interviewing for my Tips for Teachers podcast Alex Quigley, who's big into closing the vocabulary gap and so on. And we were talking about how being able to explain something verbally is probably a necessary feature before kids start writing things kind of so you look at all the examiners reports where you ask kids to explain, discuss, describe. They're pretty bad at them at GCSE. So it's only by doing tasks like this where they're getting used to, I think this because giving them all little verbal stems, that you've then got any hope in them getting right and extended sense and stuff. Love that.
Yeah, and it's interesting, it's so easy in a maths lesson to take one-word answers, short answers. It's really, that's the thing I'm working really hard at improving in my teaching, because there's been quite a national focus on oracy, or certainly at my school last year, it was kind of all we talked about was oracy. So it's something where, as a maths teacher, you could dismiss it and say that's something for English teachers, or you could say actually massively important in our subject.
I agree.
This is Don Stewart.
I'm going to say now, this top 5 resources of all time.
Amazing.
Big claim, but I'm going for. I think it's brilliant. It's absolutely brilliant.
Yeah, he says work out the areas and then work it out in another way. I think pretty challenging for students. Like, this is something, again, as a teacher, I look at it and I think I never really thought about it before, but I understand this. But for my students, they're gonna have to really conceptually understand what's going on.
So I'll tell you 2 things I like about this, right? So reason 1, he doesn't have any dodgy triangles.
Yeah,
like
they're all Pythagorean sound.
They're all legit. So that's big tick for Big Don, number 1. But also, as I said before, anything where kids have an opportunity to do things 2 ways, the fact that they get the same answer, you've got a bit of a self-checking mechanism in there, but you've got that moment of awe and wonder, because they're like, why the hell, if I multiply these 2 numbers and these 2, do I get the same thing? That
really
is
good
brilliant.
task.
Brilliant.
I think a student who, if they're not well prepared for that, they're going to just be seeing like, what's going on with the 2 right angles? Like, really, like, quite a deep conceptual understanding needed for that.
It's brilliant.
And then just on oracy, I say, like, very often my students will say, I'll say, how do you find the area of a parallelogram? And they might say base times height. Actually, normally they'll say, I don't know, because they never remember that. But if I say, how do you find the area of a triangle? They might say half base times height, or base times height divided by 2. And I will always correct them. And I'll say, I'll say you need to say base times perpendicular height, or altitude. So the point on oracy there is correcting students and getting them to say it again. So if they say base times height, you say, right, base times perpendicular height. You need to say that. You need to put that word in just to really emphasize, so they remember they need to find the perpendicular. And if they keep hearing it and keep saying it, then they're more likely to remember it.
sorry for interrupting. I'm a bit obsessed with this at the moment. I think there's a difference between these two things, right? So let's imagine I've said to you, what's the area of a parallelogram? You've said base times height, right? Option one is I say to you, you've forgotten to say something there, and you say perpendicular, and that's okay, fantastic. I don't think that's anywhere near as good as me saying, okay, you've forgotten something there. You say perpendicular, and I say, no, put it in the full sentence.
Yeah.
They have to stitch the thing
You have to
together for it to
absolutely.
stick.
Yeah, I agree. Again, it's something that doesn't necessarily come naturally to me in the classroom. It's something that I'm getting better at. Yeah. This one is just a little bit more on depth here. This one is from Paul Rowlandson, and it's just that idea of thinking backwards and being given a coming up with your own examples. So yeah, given the area is this and the perimeter is this, and you know, if it was a rectangle, it would be a totally different question. It's things like that. So I mean, for parallelograms, Paul Rowlandson's blog post about it is full of depth ideas. Last thing on the challenge, and again, this might be something for a maths enrichment club, not necessarily for the classroom. Are you familiar with Heron's formula?
No.
Sometimes called Hero's formula.
I've never seen that in my life.
You've never seen it. So it's a really, really interesting formula where you can work out the area of a triangle using this formula. It involves the semi-perimeter. Semi-perimeter is just half the perimeter. Okay, so you just do A plus B plus C divided by 2. Right, okay. Once you've got the semi-perimeter, which is just a number, then you can use that formula where you square root the semi-perimeter multiplied by the semi-perimeter, take away A, semi-perimeter, take away B, semi-perimeter, take away C. That's really complicated, but is used in real life. I was once in a taxi, and the taxi driver, I was in Edinburgh, and the taxi driver said, oh, you're a maths teacher, blah, blah. They always talk to you about being a maths teacher, and he said something to do with how his granddad worked out the areas of land around Edinburgh or something using Heron's formula. So like this is something that I don't know if it's used widely now, but certainly there was a time where people used this to find triangle areas because you don't have to use trigonometry for it. And it's actually, once you know how to use it, it's really quick. In fact, someone I think on Twitter might have told me that they teach this they're a maths teacher teaching, I think, people in the Navy or something. It was like some kind of army school, and they teach Heron's formula now. Yeah. Good so God. Like there's definitely something that it's useful for maths teachers to know it exists. It's also really good in a lesson on substitution. Yes. So even if you're not teaching area, if you're doing an area on substitution, it's like, right, here's a complicated looking formula. And look, all we're doing is substituting 3 numbers. And you can then work out areas. So, but also just to show you that you can also make this like into a really interesting challenge question. A triangle's sides are given as 2y, 2y plus 2, and 4y minus 2. Its area is y root 10. Find out the value of y. The best way of doing that is some lovely surd work using Heron's formula. Jeez. I wouldn't do that in a lesson necessarily, unless I was like substitution or really trying to challenge a class, but I could do it in an enrichment group.
Flipping heck. Heron, there he is.
Yeah, interesting. So, you know, there's other, like, you know, area mazes everyone loves.
These were big. Like these were trending.
I mean, I've got the area maze app on my phone. It's really challenging, and there's area maze books. These ones are Don Stewart. And the thing with this is, if you say you don't want to use fractions or decimals, people think you can't do it without a fraction or a decimal. Like if you look at that one, like how do we find that question mark at the bottom on that one on the left? Then a lot of people will say, we'll say that it can't be done without fractions decimals, but actually it's just a bit of reasoning. Like in this one, you'd say, I can work out that bit at the top because that is, you can work out the dimensions. That's 3 by 1. And then you can say, right, once I know that, I know the area of that whole bit at the bottom. And then I can see that bottom area is double that top area. So that must be a 10. So all of this is reasoning. And it's so if you want some reasoning tasks in area, it's lovely. That's Don Stewart, but you can get them all over the place.
Nice. Yeah, love it.
So anyway, I have my final point on this whole thing. So this is, I have literally just scratched the surface of area. I said I'm going into depth, and I've gone into depth on 2 little bits, which just goes to show how much you can go into depth on any topic. We've looked at history, curriculum, assessment, and then we've just chosen 2 bits of pedagogy to look at. But there's absolutely tons you can do here. And the thing that's nice about area is the development of reasoning skills. Like it's a huge job. Some topics, there's, you know, particularly with algebra, I think there's less opportunity to do a lot of problem solving and reasoning, but area is just full of it. So really, really wonderful topic and lots for teachers to explore.
Love it. Love it. So in summary, just a couple of things. Firstly, just a reminder, if you want to access these resources, there'll be a downloadable link wherever you got this video from. Also, Feel free to check out our other Topics in Depth sessions. We've got them on loads of different topics, all the similar kind of thing. Hope you find them useful. A massive thank you to AQA for kindly sponsoring us and enabling us to do this. And of course, little plug. Jo's not very good at plugging her work, so I'll do a bit on Jo's. Jo's got a wonderful book on mathematical methods. If you teach a certain topic in a certain way, have a look in this book, because there'll be 3 or 4, if not sometimes 10 ways that you won't have thought of. And again, goes back to what we're saying in this session. If you can show kids more than one way to get the same answer, it's such fertile grounds for discussion. So if you haven't checked out Jo's book, Mathematical Methods, and I've got a book, Tips for Teachers, out as well, that you might want to check out. Jo, as ever, always been a pleasure, and I'll see you on another Topics in Depth soon.
Thank you, Craig.